In part 2 of our exploration of discriminant function analysis with SPSS statistics, we're going to return to our earlier example, but this time we're going to investigate a few other interesting options that might prove useful with regard to model building. We're also going to look at generating predictions within the data itself. So returning to our earlier example and picking up from where we left off, we're going to call up the discriminant function procedure again by going to Analyze, down to Classify, and choosing Discriminant. And you can see here is the same dialog that we used previously. It's still populated with the same settings and same variables that we used from our last run. But on this occasion, we're just going to explore a couple of other options. The first thing we might want to look at is here under the Classify button. We open up the sub dialog associated with that. You'll notice that we have our default option here where all prior probabilities are based on all groups being equal. And in that case, because we have three groups, that means that each group is an equal chance, which works out as a prior probability of 0.333 or a 33.33% chance of being included in one group or the other. Irrespective of the fact that one group is much smaller than the others, we can actually ask it to compute from group sizes and see what the effect is of that. So this time it's going to change the prior probability. So if one group is more popular than another, then obviously the prior probability, the chance of being included in that group, is greater than if you're in a much smaller group, such as the custodial, which only has 27 cases. Let's click continue and see the effect of that. Run it again. You should find that this time when we look at the bottom, the overall classification rate now is 90.9%. So that looks like that's actually got a bit better. But when we investigate the individual classification rates for each of the groups, we can see that custodial now is only classified with an accuracy of 40.7%, whereas clerical is classified at an accuracy of 97.5%, and managers at an accuracy of 78.6%. So the other two groups have lost out in favor of the clerical group, which has 354 cases. We have effectively biased it towards that group. When we look at the cross-validated values here, we're getting very similar results: 37%, 96.7%, and 78.6%. If we compare that to the previous classification result, we can see that the all groups equal setting here meant that we were 84% accurate overall. With the compute from group sizes, that accuracy has gone up, but we can see that the custodial group was previously classified at 92.6% accuracy. Now that's dropped to 40%. So that's, worse than half. Here it's 82% for clerical, but that's jumped to 97%. And for the manager group, that's falling from 86.9% down to 78.6%. So it's really a practical question here of which groups are you particularly interested in accurately predicting? Are they all equal and equal in terms of importance? Or do you want to go for more accuracy overall? Returning to the output itself, we can see that indeed the prior probabilities in this new setting are now reflective of the different group sizes. The probability of being in the custodial group has now fallen to 0.057, whereas the probability of being in the clerical group is 0.766, and the probability of being in the manager group is 0.177. Let's look at another option that we might want to explore here, which might have an effect upon the accuracy of the model classification. Let's go back to the discriminant function procedure. This time we'll just use the dialog recall button, call that procedure up again. This time we'll go to Classify and switch back to all groups equal. This time, however, we're going to use a different setting here under Use Covariance Matrix. This is something that you might want to explore if you suspect that the lack of equal covariance, which is indicated by a really significant result in the boxes M test, is affecting the accuracy of the model. You can actually switch to this different method here, which is where separate groups are used to compare. Each individual group is used to create its own covariance matrix. So we're not looking at a pooled covariance matrix, but we're creating separate covariance matrices for each of the groups. And it may have an effect upon the accuracy of the model. When you do switch this option on, you may notice that the leave out one classification option is then grayed out because it doesn't apply to that. Let's click continue and see the results of that when we look at the classification table at the end of the output. So it runs that again. It doesn't really have a big effect upon things like coefficients, etc. But when we look at the bottom here, we can see that the classification results are markedly different. Let's compare them side by side with the original classification table that we were getting from our first run. And here we can see the original within groups covariance matrix with all groups equal probability at the start, and we can see that the accuracy level within the original table here is 92.6% for custodial, 82.6% for clerical, and 86.9% for manager, giving us an overall average accuracy of 84%. Whereas with the separate groups covariance matrix that we've just switched on, that option, we now have 96% accuracy in custodial, 89.8% accuracy in clerical, and 97.6% accuracy in the manager group, and that gives us an overall accuracy rate of 91.6%. Now, irrespective of whether or not this is actually reliable, given the fact that we've got quite small sample size here with the custodial group, and indeed the manager groups, not the largest sample size we can deal with. Most people would say it's not really worth switching to the separate groups covariance matrix unless you're seeing a markedly improved accuracy in the classification results, assuming that maximizing the accuracy in the classification results is your goal, as opposed to trying to estimate the parameters of the model most accurately. In this case, however, we are seeing a fairly big difference here between 84% and 91.6%. So there is some merit, it could be argued, in using this particular setting over this setting. In the next section, we're going to now return to the procedure itself, and we're going to look at a way in which we might try to get a better handle on where the true coefficients that we're estimating might lie by using a technique known as bootstrapping. So again, we return to the SPSS data editor, and we're going to call up the discriminant analysis dialog box. Here it is as before, but this time we're going to click on bootstrap and ask it to perform bootstrapping, which will allow us to calculate 95% confidence intervals based on the data. Bootstrapping resamples the data multiple times. It's a very resource intensive process. If we click on bootstrap here, you can see it's going to take 1,000 samples, and it's going to give us a range of values akin to 95% confidence intervals, where it's going to show us where 95% of the coefficients that it produces lie within. So we'll be able to see the minimum coefficient, the bottom boundary of that, the bottom 2.5% and the top 2.5%. Click continue. Before I do that, however, I'm going to go to statistics and actually call up some function coefficients, of which we'll talk about in more detail later on. But I just wanted to show you that these two options here are also affected by this. If I click continue and click OK and run the procedure again, down along the bottom here it says it's running discriminant, and it's going to resample the data multiple times, 1,000 different samples as it performs the bootstrapping. As I say, it's a resource intensive process, so we'll just wait until it finishes and then we'll have a look at the results. Now that procedure has completed, we can see that we get the same statistics as beforehand, group statistics. As we scroll down, test by quality of group means they aren't affected by the bootstrapping process, nor is the box's M statistic, which is still significant, showing that we have violated the covariance, equality of covariance assumption. The canonical discriminant function values that we're getting here, the eigenvalues and the canonical correlations, are still the same as before. But as we continue to scroll down, we get to the standardized canonical discriminant function coefficients. These are effectively the beta values that we mentioned earlier on, the partial correlations. And we can see that for current salary here against function 1, we have a coefficient of 0.6, and against function 2, 0.61. But looking across here at the bootstrap results, we can see that this value could potentially, if we were to resample the data again and again, could be as low as 0.395 or as high as 0.797 or as low as 0.408 for the function 2 dimension and as high as 0.831. So we get a sense of how reliable these coefficients are, assuming we were to repeat the sample again and again. Also of note is the fact that the weaker partial correlations, such as here with beginning salary with a score of minus 0.150, very close to 0, that means that the 95% confidence intervals are showing that it could be a positive number or a reasonably strong negative partial correlation value here of minus 0.54. This is true for anything which is going to be quite close to 0. So here we see age of employee, very weak partial correlation here of 0.056. And as a result of that, the 95% confidence intervals again are a minus number here of minus 0.024, could be very close to 0, or as high, in inverted commas, as 0.130. Other coefficients are also affected by this. We haven't seen these coefficients before, but I've asked for them now, and we're going to talk about them in a little bit more detail in the next section. But here we have the canonical discriminant function coefficients. These are equivalent to a regression equation, if you like. These are the values we would use in order to compute the actual function scores. As a result of that, we have a constant added on the end here. So if we were to multiply age by this value, education by this value, same for minority, all for function 1. Current salary here, it looks like it's 0. It isn't actually 0. It's actually a really small number, and we can show that if I just increase the decimal places here. See, it's actually just a really small number, which is affected or a result of the fact that the salary values are measured quite large numbers. You know, the scale of the numbers is much larger, so as a result of that, the coefficients are quite small. But we can see that when we look across here, the intervals themselves, again, they could be positive or negative when we look at the 95% confidence intervals. And we're seeing this across some of these variables as we're looking down through them. Let's just look at these ones and again see if we can increase the size of the number of decimal places that we're viewing here. So they're all positive apart from this one here, beginning salary. It's a negative coefficient or a positive coefficient. So anything where, you know, where the value could be positive or negative means that it could be 0, because it's, you know, it's bounding that threshold. So it could be that, you know, it really has no effect at all. And it's just an indication of how reliable those coefficients are. So bootstrapping is a very powerful way for us to try and estimate where the true coefficients are likely to lie, how reliable those coefficients are, and look at the range of values that they could possibly occupy across 95% of the distribution of possible estimated parameter values. In the next section, we're now going to look at how we actually can get discriminant to predict the values themselves. How we can apply the model to new data, and how we can get it to save out our predictions for us. So again, we're going to run the procedure using the dialog recall box button here. Calls up that dialog. Earlier we had switched on the bootstrapping procedure. I'm going to switch that off. That option's now switched off. I'm going to draw your attention just to two of the statistical outputs that I'd requested in the last run here. I'd ask for what are called Fisher's function coefficients. I'll return to that in a moment. That's kind of an easier way for us to create coefficients that allow us to apply the model to new data using a formula. But we've also seen the bootstrapping produce coefficients with 95% confidence intervals around the unstandardized coefficients. The unstandardized coefficients are what are used to create the function scores themselves, which the system uses in order to classify the cases. And if you want to see those function scores, you can simply click on Save here and switch on discriminant scores, click Continue and OK. it runs the procedure once again, and if we look down here at the canonical discriminant function coefficients, these are the coefficients which allow us to create our discriminant scores. If we just double click on this, we'll be able to see them in a bit more detail by asking it to increase the number of decimal places shown. So if we multiply each field or each variable by these scores for function 1 to begin with, and then add on a constant at the end, we'll get a score for function 1. We'll do the same thing for function 2. And that produces effectively these two columns for us, which are discriminant function 1 and discriminant function 2. These are what are actually plotted when we see this plot here. These are the actual scores, the dimensions, and this is where the cases lie within those dimensions, with the centroids computed as well. So that's one way in which we can get it to produce predictions for us, though obviously would then have to be a bit tricky for us to then try to use these discriminant scores to actually calculate or predict which group each case belonged to. And as a result of that, there is an easier method. That's really what the other method here, which is you remember I asked for this Fisher score. I went to statistics here and I said ask for Fisher's function coefficients. They create this table, which is this classification function coefficient. Again, we are seeing coefficients here, and we are seeing a constant added on the end. But this time, instead of coefficients for function 1 and function 2, we're seeing coefficients for each of the different categories that we're trying to predict. And it turns out we can use this formula, a kind of an approximate formula, if you like, to calculate a score for custodial, to calculate a score for clerical, and to calculate a score for manager. And basically, whichever score is the largest, we can then assume that is the prediction. That's the group it's trying to predict. So if the score for clerical, if the clerical column is the largest, then we predict it to be clerical. If the score for custodial is the largest, predict it to be custodial. If the score for manager is the largest, we can predict it for manager. Just as an example, I've got some syntax here which I'm going to run, which shows you how we can create these scores, these predictions, if you like, these classification function scores using these Fisher's coefficients. Just have a look at that. And here in the syntax editor, I've copied and pasted each of the coefficients. I've rounded them slightly from that Fisher's coefficients table with a constant on the end. And I've asked it for each of the columns, for each of the three predicted groups, to multiply the respective coefficient by the predictor variable. So this is the coefficient for custodial by salary, plus the coefficient for beginning salary, plus the coefficient times the values of education, plus the same for age here, coefficient for age times age, and the coefficient for minority times minority. And then we've just added on the constant at the end for each of these. You can see that this is going to compute out three different columns: custodial, clerical, and manager. What's that look like if I just run that? That creates these three columns here. And as you know, the column with the largest value, which here would be manager, would be the one that we would predict to be the class that case belonged to. If I run the rest of the syntax, you can see here I've just got another little compute where I'm creating a field called prediction. And it simply says, look, if the score for custodial is greater than clerical and the score for custodial is greater than manager, then predict it to be in group 1. We do the same thing for clerical. If it's greater than custodial and greater than manager, predict it to be group 2. And lastly, for manager, if that's greater than custodial and the score for manager is greater than clerical, that's group 3. We attach some value labels to that, and that's simply going to create our prediction here at the end. So these are our predictions. That's how we could pick up the formula, effectively the coefficients from the model itself using Fisher's coefficients, and apply it to a brand new data set. Another way to do this would be simply to go to discriminant analysis and ask it to save the predicted group membership. And we could even ask for the probabilities of group membership here. If I click continue at that point and click OK at that point, Here we have the scores should be exactly the same. Here's the predicted groups. You can see they're pretty much exactly the same. I've tested it, they are the same. Here are the probabilities of being in group 1, group 2 or group 3. You can see why it's been assigned to group 3 because it's got the highest probability. You may get a few where the probability is quite split. Here, for example, it's predicted to be clerical and custodial. There's a tiny difference here because the probability is slightly different. So I'm rounding somewhat, and probably because I've rounded it. Here it's predicted to be custodial, here it's clerical. That's because the probabilities are so close together. You can see that's, it's 49.728 versus percent chance versus 50.254% chance. So you're going to get some slight differences, of course, when you're using coefficients and you're not using all the decimal places. Another way in which I could do this, if I just delete these, is I could add cases on to the end here. So I could just add on the next case. If you imagine this was a case on the end here where we didn't know, we've added case number 471. We could do the same and just append a bunch of cases onto the end here. If I ran that where we don't know the outcome, and again I'm asking it to save group membership and the probability of group membership, click continue and OK. If we then go down to that case, you'll find that although we didn't know what class it belonged to, which job category it belonged to, it still creates a prediction for us and it produces probability scores for us. So these are different ways in which we can pick up the model and apply it to a new data set. One is simply by adding new rows onto the data set and asking the model simply to save the scores out. It will apply it to the new rows. Another one is to use the Fisher's coefficients to create a formula which we then can apply to a brand new data set where the target variable, the target categories are unknown.